Hello class, welcome back to Chemistry 3120, JP here. Today's lecture 28, and over these next couple classes we're going to talk about the stereoselective reduction of aldehydes and ketones. So let's get started. A lot of this material can be found in chapter 33 of your textbook. And we're going to divide this section up over 2 lectures. So in terms of an outline, we'll look at stereochemistry of this reaction. We're going to look at something called the Newman projection of aldehydes and ketones. And once we understand that, we're going to look at the effect of electronic substituents and chelation effects on stereochemistry. Okay, so I'm going to divide this up into 2 chapters, or 2 lectures. So what we'll focus on today will be introduction to the stereochemistry and look at Newman projections and how we can use that to predict the stereochemistry of this type of reaction. All right, so definitely we've done a lot of work and we've done a lot of reduction, we've looked at a lot of examples using reduction. So let's take a look at a sort of a classic example. So if we take this compound here, and if I ask you to reduce this with sodium borohydride, we've gone through this mechanism many, many times, and you know that you're going to have hydride attacking here, and then the O- will pick up a proton. So you're going to end up generating an alcohol. But one thing that we haven't talked about is that after the reduction, we actually generate a new stereocenter. This carbon here will have a hydride attached, you'll have this alkyl chain, and then have another group here, and then the alcohol group. So there'll be 4 different things attached to it. So in fact, during this reaction, you can generate 2 different stereoisomers. So let's take a look at what those 2 stereoisomers look like. So you can have a situation where your hydride could attack from the top, or going this way, thus forcing the alcohol to go into the board. And you'll generate this product. The other stereo product would be where this is flipped the other way. So you could also generate that product. And those 2 are both stereoisomers of one another. So, all right, that's interesting. Let's take a look at another example, a similar example, but different nevertheless. And what if we take a look at this compound here with a stereo-defined center? Rather than having a ketone, let's take an aldehyde and let's use a Grignard reagent to have this react with. So what if we treat this with methyl magnesium bromide and something like THF? So you know that methyl magnesium bromide is really going to be like a CH3 minus nucleophile. So this can attack here, and you can imagine it could attack from this side or from the board. So you're going to generate two different stereoisomers depending on which side it attacks on. So after workup and after the O- picks up a proton, you're going to generate a couple different isomers. So let's take a look at what those look like. So if attack comes from behind the page, let's put our methyl group like this. Our hydroxyl group will now be pointing towards us, and then we'll have our hydrogen like this. And the other stereoisomer will be where the methyl group comes and attacks from the page. The OH will be in the page going away from us, and then the hydrogen within the plane of the page. These structures are both stereoisomers of one another, and they're both drawn correctly. However, when we're dealing with stereochemistry, in particular when we're talking about linear chain alkyl chains like this, it's convention to put the longest carbon chain in the plane of the page. Okay, so you can see here you have this phenyl group, carbon. These carbons here are in the plane of the page. So if we want to put the longest carbon chain in the plane of the page, you can see that we need to do another thing. This methyl group is pointing away. So what do we have to do to this group here in order to get the methyl in the plane of the page? We need to rotate this in such a way that this will now come down. Okay, so you can imagine we can rotate this 60 degrees. If you rotate this carbon-carbon bond, this carbon group will come here, this OH will go behind us, and then the hydrogen will now be pointing towards us. Okay, so if we rotate, the product will look like this. The methyl group is now in the plane of the page, so all the carbons are in the same plane of the page. Okay, so rotate to put longest carbon chain in the plane of the page, or in this case, the whiteboard. Okay, so if we look at this example here, we have to do the same thing. So rather than turning it 60 degrees clockwise, we're going to turn this 60 degrees counterclockwise, and that will put this carbon in the plane of the page. The product will look like this. Okay, so these two are your two stereoisomers. And the way that we denote them is that you can see that the two substituents, the methyl group and the OH group, they are on opposite sides of one another. So we call this the anti-product. Whereas in this case here, we have the methyl group and the OH group on the same side, right? And the two hydrogens are on opposite sides. So in this case, we call this the syn product. We can use and apply the same principles up there too. So let's take a look. This one here, you have the methyl group and the OH group on opposite sides. So this is the anti-product. And over here, you have a methyl group and the OH group on the same side. So this is the syn product. So the question is, well, what are their relative distributions to one another? Are they created equally, 50-50 mixture, or is there some inherent ratio of a major to minor product? So if you actually do this reaction, you will get a 3:1 ratio of anti to syn. Okay, so major product This one is minor. Okay, so the anti is major, the syn is minor. In contrast, during this reaction here, we actually get the anti as our minor product in a ratio of 1 to 3. So the syn product is the major product. Okay, so now that we've introduced stereochemistry, how is it that we know what the ratios would be without doing the experiment? Is there a way for us to predict what those ratios would be? So the answer is yes, and let's take a look over on this board, what that will look like. All right, so we're going to look at something called Newman projections. And essentially what we're going to do is we're going to take a look at this last example that we stopped here. And we're going to treat this, again, with methyl magnesium bromide. How can we understand what this looks like when that methyl group attacks? So what I want you to do is I want you to take imagine you are in the plane of the page, okay? And this is that's your eyeball, okay? And you're going to look right through this bond here, right through this carbon-carbon bond. And I want you to draw what you see as you go through this carbon-carbon bond. So what we see is this aldehyde, right? You have this carbonyl group on the top and this hydrogen on the bottom. Okay? And here is the carbon focal point. And if you keep going through that carbon-carbon bond, and as you make your way, you're going to see that there's a phenyl group that's right behind the carbonyl. Okay, so let's draw on that phenyl group. As you look at the phenyl group, it's pointing up. The methyl group is pointing towards you. So that's going to look like this. And then this hydrogen is going to be over here. Okay, so I want you to understand how we get from this structure to this Newman projection. All right, so I realize, okay, well, I'm going to go back to this slide in just a second. But before we do that, I want you to look at this molecule here and ask yourself a question. Do you think this is a true representation of what this conformer looks like in solution? If you look here, you can see that there's very likely some steric clash between that phenyl group and then the oxygens of that carbonyl group. So knowing that this bond here can rotate, is there a better way to draw this Newman projection? Is there a lower energy conformer that would be more stable? So the answer is yes. So let's take this big bulky phenyl group and let's orient it, in fact, 90 degrees away from the carbonyl group. We want to keep it 90 degrees. We don't want to sort of clash with this hydrogen as well. So let's take a look at those two energy conformers. So if we rotate this until we hit 90 degrees, what will that look like? The phenyl group will be over here. This methyl group will now be over here. And then this hydrogen will be up here, all right? So we've placed the large group 90 degrees away from the carbonyl group. Is this the only low energy conformer? Well, no, you could also rotate this 180 degrees. And you could have the phenyl group on this side, and it's also 90 degrees to the carbonyl group. So let's do that rotation. Let's put the phenyl group over here, 90 degrees away. If you do that, you can see that you're going to have a methyl group here, and then a hydrogen down there. Okay, so these two represent the lowest and more stable lowest and most energy stable conformers, and these are the dominant ones that will exist in solution. Okay, so the point I wanted to make, I'm just going to go back to this whiteboard because I realized I made a little error. So let's just correct that. So go back to your notes. And when I was talking about doing a rotation, in order to get this carbonyl or this carbon into the longest plane of the page, we talked about rotating it, okay? But a full circle rotation, right, is 360 degrees, okay? So if we're dividing that by 3, in fact, the rotation angle has to be 120 degrees. So I apologize for that error, but that's easy to fix. So you rotate this 120 degrees, so a third of a circle, which is 360 degrees, and you'll get the right product. Similarly, over here, we have to rotate this counterclockwise, not 60 degrees, but 120 degrees. All right, so we can go back to here, and what we can do is, let me just write that we want the phenyl group is largest reorient this 90 degrees from the carbonyl and the hydrogen. Okay. So how can we use this information to help guide us in terms of what the reaction will look like and what the stereochemistry will in fact look like? So before we do that, I'm going to redraw those two low energy conformers. Okay, so all I'm doing is I'm just redrawing these two over here because we are going to use them. So now that we've established this, we need to figure out how the nucleophile is going to attack. In this case, it's methyl magnesium bromide, but we could just arbitrarily call this a nucleophile. So there's something called the Bürgi-Dunitz angle. And this is basically a calculation to try to understand which angle the nucleophile attacks the carbonyl at. All right, so here's your carbonyl group, and you know that there are these p orbitals. And if we're going to add something like sodium borohydride or any nucleophile to a carbonyl group, how does it actually attack the carbonyl? So it turns out that, and I'm just going to kind of draw this plane here. So just a dotted line, just so that we can see the plane. If we try to take a nucleophile, if we try to attack directly 90 degrees to the orbitals, you don't get good bond overlap, and that's not appropriate. Similarly, if you try to attack exactly in this direction here, sort of flat at 180 degrees, that doesn't work either. And so therefore, similarly, if you take the nucleophile and attack it from above, it can't come down from 90 degrees. In fact, the correct and exact angle at which it attacks is from this orientation. So here's your nucleophile, and it can attack like this. And if you actually measure the angle at which it can attack, this angle here is 107 degrees. Okay, so this is 90, so it's just a little bit more, 107 degrees. So the nucleophile can attack through this position, and it can also attack 107 degrees from this direction as well. Okay, so this is okay, and this is also 107 degrees. Okay, so this is basically done through crystallography studies and theoretical studies trying to understand the angle of attack. This just summarizes what I said. Theoretical crystallography shows that the angle at which a nucleophile attacks carbonyl is at 107 degrees. So let's take a look at these two conformers here. All right, so we know that nucleophiles can't attack 90 degrees. They can't attack 180 degrees. They can attack 107 degrees. So let's take a look at potential routes of attack. And maybe what I'll do, just because I'll try to use a little color. I know I drew them on that whiteboard, but I only have a black marker. Let's take a look at some potential routes of attack. So I'll go back to this board here, and maybe it will make the point clear. So here you have a potential nucleophile, right? It can't go this way, it can't go this way. This is one potential route of attack. Okay, so that's around 107 degrees. Another route of attack would be on this conformer, where you have this attacking here at 107 degrees. Where else do we have routes of potential attack? You have another potential route of attack if this nucleophile comes and attacks from this side at 107 degrees. I've deliberately drawn these three first because you can see that this nucleophile gets awfully close to this phenyl group, so there's going to be some steric clash. Same story on this side too. When this nucleophile comes here, it's going to have some steric clash potentially with a methyl group. So is there a better route of attack? And that leaves us with this last one here, which I deliberately left out. And if this nucleophile attacks here, this corresponds to the path of least resistance. This hydrogen is small. It's furthest away from those bulky substituents. So in terms of the best one to attack, let's eliminate these two. Let's eliminate this one. Let's eliminate this one. And so these are red. Not sure if that will show up on the camera. This one's blue. So this is the preferred route of attack. All right, so 4 potential choices. So let's take our nucleophile. So let's actually, in our case, take what we've learned from here and apply it over here. So this will be our methyl group, as we can think of as being CH3 minus. So that's going to come and attack right here. So draw the arrows, that's at 107 degrees. And let's draw out what that looks like after it attacks. Okay, so you're going to have methyl group down here. that just attacked. You're going to have O. It's going to be O minus, but then it's going to pick up a proton during a workup step. So we know it's going to become a hydroxyl group, just like we've shown over there. So OH, okay? And then your hydrogen is now going to come out this way. So everything has to be 120 degrees from each other. This is now an sp3 hybridized carbon, no longer sp2. And then the carbon behind it, everything remains the same. Okay? So you can see that you have this methyl group here, right? Then you have this phenyl group that's up over here, and then you have this hydrogen here. All right, so this is your Newman projection for the compound. And let's see what this translates to. All right, so maybe what I'll do is I'll go to that board and erase, because I want to keep that here. A lot of different moving parts here, for sure. This is one of the reasons, by the way, why I like using the classroom and the chalkboard, because you can kind of look and point at different things rather than it being on a screen and then you have to scroll through multiple times. So you can think of it like a big, big movie theater, big movie screen. You can see everything at once. All right, so let's take a look again, like I mentioned, at what's going to happen. So, yeah, so why don't I just redraw that, just so we have that handy. Okay, so what we need to do, did I do that right? Yeah, that looks okay. Is we got to ask ourselves if the longest carbon chain is in the plane of the page. So you can see that we have our phenyl group, and then you have the carbon, and then you have this carbon here, which is in the plane of the page. Right? So all the carbons are in the plane of the page. And what you can see here is that the methyl group and the hydroxide group, those are on the same side, right? So that means that your product is going to be syn. Okay, so if we actually draw a product in terms of what this will look like, here's our phenyl group, here's a methyl group in the same plane of the page, then all you have to do is you got to put that methyl group and this OH group on the same side. Okay, so this is your syn product. And through this conformer that we learned through Newman projection and the angle of attack, we can now understand and rationalize why this is the major product. Okay, if we look back down here, and I told you that this is the major product, and yes, it is. Okay, so now you understand why. So this type of model here is actually called the Falcon and model, and it really just describes the Newman projections and how we can understand which stereoisomer is going to be formed in excess, and it's all based on that Berge-Duguitz angle and which side that nucleophile attacks. Okay, so it's not a perfect reaction. Syn is a major product, but you also learn that you get some anti-minor as well. So it's not 100% stereoselective. Okay, very good. So we can, so we can do a little bit of summary of what we learned. And essentially, what I think I'll do is erase this whiteboard here. case, we were looking at the lowest energy conformers, where you have 3 different substituents on the carbon adjacent from the aldehyde that was attacked. So here we're going to look at the lowest energy conformation of a carbonyl compound. So in this particular example that we spent a lot of time on, we have 3 different groups that differ in their size. We can call this phenyl group large, we can call this methyl group medium, and this hydrogen small. So if we do that, let's call L is equal to large, M is equal to medium, S is equal to small. So what we can learn from this exercise is that when you're drawing your low energy conformers, and actually let's just put an R group here because this could be a ketone. Okay, so switch that to an R group. What you're going to do is you're going to orient your large group, the largest group, whatever that is. Maybe it's a methyl group, if perhaps some of these other substituents are smaller. Or maybe it's a huge, naphtha group with all these different side chains attached to it. So you're going to put the largest group 90 degrees away, and you're going to orient the other groups respectively. So this is one low energy conformer of what it would look like. You'll rotate that 180 degrees, and the other low energy conformer will look like this. Okay, the 2 low energy conformers. And as you've learned, the nucleophile will pick the path of least resistance. So in this case, you look at the size of your different groups. You know it's going to attack at 107 degrees, so the best one is attacking this way. Okay, so that concludes our lecture today on the introduction of stereoselective reduction of sodium, of aldehydes and ketones. We've looked at a few examples here, and what we're going to talk about next time is the effect of electronic substituents and the chelation effect. So see you soon for that one. Take care.